Okay. So open up our chat. All right. Couple of administrative kind of details, and then we'll get right into it because we have a lot of fun stuff to do today. Don't forget, you must sign up for your final exam by Friday. So do it by Friday. Well, you actually have all day Friday, but don't wait that long. Do it right away so that you're done with that and are comfortable with it and all that good stuff. If you have any questions, please reach out to me and we can walk through what makes the most sense for your situation. So it's a quick, I've had a couple of students do it. It's a 5-10 minute conversation and we can get you set. So I want to make sure you know what you're doing for that situation. All right. We had a weekly practice this week that not a lot of people remembered to do, I'm afraid. So there was some issues with thinking about image formation and lenses. So please review that material. Your weekly practice should be provided to you afterwards, so you can kind of go back and look at some of those questions, but do look at some of that material. You do have suggested readings you can look at, and then just playing with some of the ideas that we talked about. Okay, any sort of burning questions before we get back into image formation and lenses, looking at the concave lens, and then we'll do some nearsighted, farsighted stuff today, so vision stuff, and then move into mirrors and maybe color by the end. So it's gonna be a fun day. So any questions on that? All right, I am gonna ask a question before we get started, because my little window, and I only get a tiny one on Teams, is showing like only from my shoulders up, but my Zoom window is showing everything. So can somebody tell me if the Teams, because I record with Zoom and Teams is our thing, do you not see like below shoulders? Well, that's no good. So I guess we will go with, that's very, wait, I think I understand the problem. Glad I asked, because I think Teams is using the wrong camera. So now I just have to fix that. Indeed. Aha! Now we're in business. All right. Okay, that should be good. Oh, let me get my chat back up in case anyone has questions. Okay. So somebody let me know if that has fixed the problem. I think it should have. Better. All right, good. Thank you. Okay. So let's look at, yes, we are fixed. Good. We are going to start with our convex concave lens today. We've already dealt with image formation in the convex lens, and we're out of focus apparently. There we go, back in focus. So remember the concave lens. This is the one that's sort of bowed inward, so it looks like a cave. And when we look at that with our laser ray box, where we see the lights produced with the concave lens, that's the physical description, but it also has that operational definition. And that operational definition describes how the light rays behave when they go through the lens. So here is our lens, and as a reminder, the light rays going through the lens are spreading apart. So those light rays are getting further and further apart as they go, after they emerge from the lens. And we said that, well, in order for a true image, a real image to be made, by definition, those light rays need to converge. And so real images must not be made using a convex lens. It can't be, because those light rays are never going to converge. Real images have to have rays of light converging, and therefore then they can reproduce the image on a physical screen, eyeball, film. So that right there, knowing that they diverge, tells us we're going to get that other type of image, the virtual image. So it's all an interpretation of what we see. So how do we get that virtual image? And then how does changing the location of the object affect both the image size and the image location. So we're going to follow the same process that we did for the convex lens. And by all means, please review that process. There's also not only our class lecture, but a mini lecture on that. So here is our optical axis again, as a reminder of some of that vocabulary. And then here is our lens. We're going to look at three different object positions. Now, even though these light rays don't focus the parallel rays of lights to a common point, which we defined as the focal point in a convex lens, based on the curvature of the lens, which influences the focal point, right? We looked at that. They do have what we call a focal point. And if the objects are similar, if the two sides of the lenses are similar or symmetric, the focal point will be the same on both sides of the lens. And I'm just going to choose a focal point. So we're going to say this lens has a focal point at those locations. So they're all the same. Now, we talked about using what were called principal rays of light to define where an image is located. So here is our object. Here's our object. This, from the distance between the object and the lens, is the distance of the object. When we're dealing with the principal rays for a concave lens, the first ray that we can look at, I'm just going to extend this lens because we're going to imagine these are infinitely tall lenses. All right, parallel rays of light. So parallel to the optical axis, parallel rays of light are refracted in line with the near focal point. So here's the near focal point. That parallel ray of light will be refracted in line with that focal point. Rays of light in line with the far focal point. So this is where my drawing gets a little junky. So that's in line with the far focal point. They're refracted parallel. So if this lens wasn't here, this ray of light would go through the far focal point. It hits the lens and is refracted. It's refracted out parallel. All right, now the third ray of light is the one that is in line with the dead center and it remains unrefracted. So that one we can or can't draw. It does, or we have to or we don't have to. It doesn't matter. We don't need it because we're going to use two rays of light to identify where the image might appear. So, and I'll get to that question in just a second. So if I extend these two, where they intersect is the image. And this is the distance for the image. So, oh, the third ray, Christian asked, why isn't the third ray refracted? It's because it hits the lens at 90 degrees. And part of the reason I don't like to draw it is because you can't visually see that happening because it's not hitting this at 90 degrees. But when the lens is actually bowed, that ray of light through the bisected lens will hit it at 90 degrees. And when a ray of light hits a surface, a boundary at 90 degrees, it remains unrefracted. So that's why it remains unrefracted. And again, I don't like to draw that one. If we drew that one, it would go right through here, right at that point as well. But it doesn't look like it hits at 90 degrees visually. And so I appreciate that that can be confusing for students. So I tend not to draw it. But if this was in fact bowed, the angle it would strike that curve would be at 90 degrees. Okay, so these two rays of light, if I extend them back, and subsequently the one that goes through the center, we would see that they cross at a common point. And again, these all represent the top of the arrow. And so this is where that image is formed. Now, what do we notice about it? Well, we notice that it is upright. That tells us right away that the image is indeed virtual. So if I were looking through this lens, so if my eyeball was on this side and I'm looking through the lens, I would see an image of a tiny arrow. Remember when we looked at that lens and we put the marker behind it, it looked small. The image looked small. What we saw looked small. Why is that? Well, when my eyeball is over here, this ray of light, then every other ray of light is hitting my eye and it's refracted. Now I have a refractory system in my eye. It's a convex system. So it takes those rays of light coming in and it converges them to a common point, producing a real image on the back of my eye. Those are the same rays of light producing these ones that are divergent, these ones that are far apart from each other. Those are the same rays of light that would hit my eye if this lens was gone. And instead of this being the object, I had an object right here, this height. So the rays of light represent an object that is of that shape, that size, that height, and that distance away from the image. Excuse me, the lens, that image distance. Now, when we see it, it appears far away. And we're going to get to this when we talk about diverging mirrors also. The object appears far away. We can't see it closer. We think it's far away. Why is that? Why do we think it's far away? Well, when we see tiny images on our retina or images on our retina that represent tiny things like this, typically images on our retina that represent tiny things are things that are far away from us because image formation tells us a convex system that's in our lens. As I move the object far away, the image gets smaller. As I move the object far away, the image gets smaller. And so if I see small images on my retina, I think it's far away. Okay, that's that perception idea that we've been dealing with. All right. So what happens if I move the object relative to the lens in a concave system? So let's try it. Let's move the image further away. That was the first thing I think that we did in the last one as well. So that's about the same size. Same principle rays apply. So a parallel ray of light is going to be refracted in line with the near focal point. A ray of light in line with the far focal point is refracted parallel. And as I bring these two rays backwards, what do I find? Here was the first one. Okay, so hopefully we can see that. It's getting small and I know your screen is tiny. First thing we probably notice is that as I increase the object's distance, I decrease the height of the image. So it gets smaller. It gets smaller. Now, it's still upright, so it's still virtual. And it's still smaller than the object. So the height of the object is still larger than the height of the image, and the height of the image is getting smaller and smaller. What if I move the object closer? So instead of being here, I bring it here. I'll put it very close to the focal point. Is that the same height? I want to try to keep my heights the same. So first we have parallel rays of light are refracted in line with the focal point. Rays of light in line with the focal point are refracted parallel. And as I bring those two rays back, we see this image getting larger. So as I decrease the object distance, I increase my image height. Now, what else do we notice? We didn't talk about the image distance. So when we pull our object back, our image distance increases. It's bigger than this space. And we can see that the image distance decreases as my object gets closer. Regardless of where I place this object, the image remains smaller. It's still smaller. So the image in a concave lens is smaller than the object, the height. The magnification is less than 1. Okay, it's less than 1. And that's consistent regardless of where I place my object. That was not the case with the concave lens, remember. As I got closer, that image got bigger. And then when I got inside the focal point, it blew up, right? And became virtual. So it didn't even make a real image. Now, what if I go inside the focal point for a concave lens? Well, I'm just going to do that on this. Oh, we can do it on this image. What if I put my object inside the focal point? Well, this ray of light remains the same. It's refracted in line with the near focal point. A ray of light in line with the far focal point is refracted parallel. And nothing really happens different than just my general rule of thumb. As I move closer, my image distance decreases and my height increases. So it doesn't matter because we're not converging, we're not switching between being able to converge those lenses to make a real image and a virtual image. They're always diverging, we're always interpreting it. It just changes the image that we see. Changes the image that we see. All right, so for concave lenses, first, the image is always virtual. The image is always virtual. Second, as I increase the object distance, my image height decreases. It gets smaller. That was consistent with our convex lens. But the image distance increases. That was not consistent with our convex lens. Conversely, if I decrease the object distance, my image height gets larger and my image distance decreases. But most importantly, we are always upright, always virtual. So given that idea, I'm going to ask a question in the chat about whether or not we can use a concave lens to take a picture. Can we use a concave lens to take a picture? So yes or no. Can we use a concave lens to take a picture? Can we put it in front of some film and burn an image on that film? Yes or no? You guys vote. All right, I am getting plenty of answers. Awesome. No, we cannot. We cannot do that. How come? Somebody type in the chat for me as fast as you can. Maybe multiple people. Why can't we produce an image with a concave lens? It's almost just a one-word answer. Can't record a virtual image. Exactly. So images can only be produced, reproduced, burnt, seen, projected with a real image. All right. So I'm going to shift gears. Any questions on that? Again, for your perspective of your assessment next week, you don't have to draw the ray diagrams. You do have to understand how images are influenced by position. You do have to understand the difference between a real and a virtual image. That's its own concept. But having a visualization of the ray diagrams or using them to get your answers certainly is doable. So you don't have to actually draw ray diagramming for image formation. You do for refraction and you do for shadows, but not for image formation. But I at least want you to be aware that you can use that tool essentially to get any answer I might ask you about image formation in lenses. So any questions on that? We're going to talk about some complexities in the visual system before we move on to mirrors. I always like to wait a minute. And you always can just unmute if you have a question if typing is taking too long. If you were in class, you'd raise your hand and interrupt me. Actually, I wouldn't even have you raise your hand. You would just interrupt me. Okay. Let's talk then about some problems in the visual system. The first problem in the visual system is our eyeball is a specific shape. So how is that a problem? Why is that a problem? Let's take our eyeball for a moment. So here's our eyeball. There's a little outlet here at the corner, what we call the cornea. And I'm going to exaggerate it actually so I can make a bigger image. Okay, so here's our eyeball. Now, remember when I showed the picture of the eyeball, which of course is still not published because, and obviously the people in class don't care because you're actually in class, because nobody's reminding me to put it on there. I'm trying to remember, I apologize. I will try to do it right after class today. Okay, so we know that there were these ciliary muscles I talked about when we first introduced the eye. So here's our lens. Notice it's convex. It's actually not purely symmetric, but we're gonna pretend it is. And when we talk about the refractory system of the visual system of the lens, of the eye, we're actually talking about both the cornea, the front part of the eye, and the lens working together as a dual lens system. Now, why do we do that? Well, one of your quiz questions asked, where is the most refraction happening in the visual system? And it's very common for people to say, well, the lens, because the lens does the refraction. But what I want you to remember is refraction happens for two reasons. One, that curvature, the amount of refraction happens for two reasons, that curvature. And the second is the difference in the mediums. And like we talked about when we first introduced refraction, the difference between air and the cornea is larger than the difference between the viscous fluid and the lens. And so most of the refraction actually happens at the cornea. Now this has proven to be very valuable because in class I would ask you, this is when I really miss having you all with me. You've heard of LASIK surgery. You've heard of LASIK surgery, I'm sure. And in LASIK surgery, what are they doing? Well, if we think about our visual system and its function, what it is it's taking images of objects that are out here in the visual world. And it takes those objects and it produces an image on the retina. And that image on the retina is then what gets transmitted to the brain for interpretation. Well, the retina then is our screen, okay? So where I can place a screen to get a nice, crisp, clear image of whatever object is going through the system, whatever I'm looking at. Well, if our visual system isn't able to get a good image produced on the back of the eye because, and most commonly, it's not the only reason, but most commonly it's because of the shape of the eye. If the shape of the eye is such that it's narrow, so instead of the retina being in a orbit such as this, where we would get good vision, 20/20 vision, we have an orbit that's slightly narrower. So this is the back of the eye, okay? Or we have an orbit that's slightly elongated. So that's the back of the eye, all right? So the shape of the eye can change across individuals. It's part of our diversity. So if I am unable, and I'm going to talk about how we do that in just a minute, if I'm unable to get my image nice and crisp there in the back of the eye, if I instead need to bring the image closer to the front of the eye, closer to our lens system, I need to bring it there in order for it to get on the retina. Then I need these rays of light to come in sharper. Conversely, if I can't get that image to get pushed back on the retina, then I need to have these rays of light come in more shallowly. Now, how do we do that? How does LASIK help us? And then what does LASIK, of course, prevent us from having to wear? Glasses, very specific type of glasses. And how do glasses help us? So all this is wrapped up in our nearsighted, farsightedness discussion. So first, how do we do it generally? If we think about this refractory system, it's a convex system, okay? Let's remind ourselves what happens to image formation in convex systems. For a convex system, converging, as the object distance increases, the image distance decreases. When we drew those ray diagrams, the object distance went further and further away. The rays of light became more and more parallel, and the image was brought forward. I had to move my screen forward, right? The image was brought forward. I had to move my screen forward, and the image got smaller. We're not going to worry about the height right now. We're just going to worry about location. So, well, if my eyeball is a very specific shape, and let's start just with what we'll call the standard shape. Okay, so the standard shape. Then I have a problem, because if I move my object further and further away, then my image moves closer and closer to the lens. The lens, we're going to call it as a unit. And then it's not on the retina anymore. So what are some of my options? Well, one option would be that I decrease the distance of my object and my lens. I shift the whole eyeball closer, because when I decrease the distance, then my image gets pushed back, and maybe it'll get pushed back on the retina. And there are some animals that do this. They move their eyes in and out to make adjustments on where that image falls on a fixed location. The retina is a fixed location. It would be creepy if we did that. I mean, it wouldn't, because we'd be used to it. But we know that as we look from something close to something far away, our eyeballs aren't doing this. Cameras do. If you're going to zoom in on something, right, you've changed where your camera lens is relative to the film, but our eyeballs don't do that. All right, so that option's out. What else can I do to push an image back? So we're talking specifically about bringing an object far away. The image then gets pulled forward closer to the retina, and I need to push it back so it falls on the retina. Well, one way to do that is to change the shape of the lens. If I have a less curvy lens brings those rays of light together later. We did that with our image formation when we first looked at this. So less curvy lens bring the image further away from the object. I'm changing the focal length, increasing the focal length. That's what we do. Our ciliary muscles, those tiny muscles on the top and the bottom of the lens, change the shape. If they thin the lens, the image gets pushed back. If they thicken the lens, the image gets brought forward. Now, it's a little bit intuitively backwards. I think it's a little bit intuitively backwards. Our ciliary muscles actually relax when the lens is thinned. So to thin the lens, our ciliary muscles relax. To fatten the lens, as objects come closer and we want to focus on them, we need to fatten that lens. Why? Because as an object comes closer, the image is pushed back. And we need to bring it forward to get it on the retina. And so we fatten the lens to do that. And it's fattening of the lens that causes the ciliary muscles contract in order to do. So in order to see things close by, our muscles contract, our lens widens, and we see things close. In order to see things clearly far away, our ciliary muscles relax, our lens thins, and we can see things further away. Now, this has pretty practical applications, especially in the time of COVID, because we are on our computer screens so much more than we normally are. You're doing your whole lectures on your computer screen. Blah. What are you told to do when you're sitting in front of a screen for a long time? Well, you start to get eye fatigue, right? Eye strain. And so to alleviate eye strain, they tell you to look far away. Not just look far away, focus on something far away. Why does that help? Well, we're relaxing our ciliary muscles when we focus on something far away. When we're staring at our computer screen, which is right here in a near situation, our ciliary muscles are constantly relaxed, contracted. And so we get that eye strain. So that idea of looking far away physiologically is important. All it has to do with image formation, getting it nice and crisp on the back of your retina. Okay, so normally, if the system is operating in the environment that we typically operate in, then the shape of the eye allows us to have enough flexibility in our lens shape. This, by the way, is called accommodation. We have enough accommodation to put an accurate, in-focused image at the location of the retina for a near object when our lens is fat, to a far object when we have to thin the lens. But sometimes it's difficult to do that. Sometimes we aren't able to do that. As an object gets further and further away, the image is pulled forward, right? Closer. So if we have an eye that is squished, the orbit is narrower than the refractory system can accommodate, the system needs help. Because as objects move closer, this system has a problem. It doesn't have a problem for faraway objects. Because remember, faraway objects are brought close to the lens. And the retina is close to the lens. So faraway objects, the person can see very well. They are what's known as far-sighted. They can see well. But as I bring this object closer, the image in a convex system is further away. And my lens starts to fatten. But it can't fatten enough to bring that image to this retina that is too close to the front. And so it needs some help. And what does it use to help? Well, it uses a device that brings in rays of light sharper than they normally would, which of course is a convex lens. So we put a convex lens in front of the eye so that as my object gets closer, if I can't bring the rays of light forward by fattening this, I need a little help. So I get a little bit of bringing in from the lens And then my system can do the job the rest of the way. So for a far-sighted individual, we use a convex lens to correct the disparity between what my system can do and the location of my retina. Now, those of you who wear glasses, you get a specific prescription for those glasses. And that prescription is related to how much help you need, right? The larger the prescription, the larger what we call the power of your glasses, the more help you need, the more curvature is required. And so prescriptions are given as the power. Now this is different than the power we've talked about before. The power of a lens is given as 1 over the focal point. And the unit for that is what we call a diopter. So your prescription is given in diopters. Now, does this make sense? The curvier the lens, the shorter the focal point, right? We did that initially. So those light rays are brought in sharper, the curvier the lens. As this number decreases, the curvier the lens, the smaller the focal point. As this number decreases, 1 over that number increases. And I get more power on my lens, higher prescription. Well, what about if the lens, the retina is located an elongated situation relative to the functionality of my refractory system? Well, in this situation, the elongated situation, now as objects are close by objects, remember objects close to the lens are refracted further away. The image distance is bigger. So images can be put on the back of that retina. Close objects can be seen. This is someone who is nearsighted. They can see things close. But as I move the object further away, that image is pulled closer to the front of my refractory system, pulled closer to the refractory system, and pulled off of the retina. And I need help pushing it back. I can't thin my lens enough. Can't get it pushed back. And so what do? I put a concave lens in front of it. This takes what rays of light would normally come in and brings them in at a different location, at a more spread out location, as if they were closer. And they refract later, they converge later onto my retina. Similarly, the curvier the lens, the larger the diverging we get, the more power on that lens. Now, this isn't the only way to fix nearsightedness, because one other option would be to change the shape of the cornea. If I made the cornea less curvy, that's in essence changing the refractory property, making it less curvy, and rays of light come in later with a less curvy cornea. Don't so much change the shape of the lens, but we do change the shape of the cornea. And this is what's done in LASIK. I think that's how you spell it. That's what's done in LASIK surgery. They're actually shaving off the cornea to reshape the cornea to support nearsightedness. Now, the last thing I want you to know about relating to the eye and corrective lenses and corrective vision is where that point is of being able to see and being not able to see. And that crossover point is if I have somebody who is nearsighted and I have an object that's close by and I start to move it backwards, the point where they can't see, that is what's called the near point. And that's important as we look at how much curvature is necessary to help support the visual system. All right. I will warn you, and I will put up practice problems today like I have in the past. This is the most difficult test question for your assessment next week, is understanding, applying, not understanding. Understanding is pretty straightforward, but applying this idea of nearsighted and farsightedness and our visual acuity. So I encourage you to look at the couple practice problems that I will post, and then I'll also have some images for you to help you remember. So that is nearsighted and farsighted. As I erase the board, pop any questions or unmute in the chat. All right, it's kind of fun stuff. I think it's kind of fun stuff. Okay. I'm going to show you one thing. I hem and haw about this each year because it's not, oh, good, we have a question. Yeah, so I think what you're asking about, Nick, is what would a test question look like? For this, it wouldn't ask you to explain what I just explained. It would ask you to apply it. So a classic, and I'll post this in your extra practice, would be something like, you are normally farsighted on land. Well, let's just do one. Okay, so let's say that, let's start with the most basic one. If you go into water, you're swimming, and you go into the water and you can't see really well, right? There's blurry vision. Now, we talked about the reason for that blurry vision is because we operate in a situation where we are in air to our eyeball. So the refractory properties of our corneal lens system is used to air to the eyeball. Gets that image nice and crisp on our retina. I go onto water and we said, well, now the difference between the outside and the inside, the air and cornea, is now water and cornea. So the difference is less, the refraction is less. So I'll type the two in the chat. Do you become farsighted in water or nearsighted? Farsighted or nearsighted? Both are blurry, but is the blurriness as a result of farsightedness or nearsightedness? So vote, farsighted or nearsighted if you go into the water. I'm getting 5 votes. Most people are saying nearsighted. Let's walk through it and see if that looks good. Okay. So if we have our, let's draw our optical axis. Here's our optical axis. And here is our lens. And let me show you, let me pull something up real quick. Okay, so I'm going to share this image with you just as a quick reminder, and this will be something that I will post for you. It's just a recap instead of redrawing everything. Here we go. Okay, I'm going to walk you through an image that's already drawn. So this was our situation for farsightedness. Remember, we said that the eyeball is squished. So as we do really good when the object is far away, because that brings the images up. So we can get those images brought up onto the retina. But as the object moves close, the images are pushed back. As the object moves close, the images are pushed back. So that's our farsightedness. And just as a reminder, we treat that with that convex lens. We pull those images in sharper. Nearsighted is when I have that elongated, that was the second one we did. I have that elongated eyeball relative to the refractory system. And so as things are far away, this image gets pulled forward off the retina and I need help pushing it back. And so I use that concave lens to help push that image back. So the question that I'm asking is, in the situation of going into the water, what happens to the refraction of the system? Oh, what makes bifocals? Hold that thought, Ian. Hold that question, please. What happens to the system when we go into water? So let's first look at the system of an object in the air. So this is our optical situation, okay? So we're in the air, and let's get some focal points on there. Okay, so we're in the air. There's our image. So this is the location of the retina. Okay, that's the location of the retina. Now I go into water. And this doesn't change. And we're going to keep the object in the same location or we can't make a good comparison. What did we say would happen to the focal point as I go into water? Well, the difference in mediums is less. So less refraction occurs. So the focal point is extended backwards. It's pushed backwards. Remember when I took those lenses that were less curvy, less refraction happened? Well, this is kind of like less curvy because the difference has gone down. So now let's say the focal point is here. Let's move back. So there and, oh shoot, I'm inside. I don't want to be inside. Let's say it's here. So there and there, just because otherwise I'll be inside. This is still my retina. This is still, parallel rays of light are still refracted through the focal point. My focal point now has changed. Oh, I hope those colors are different enough. And the near focal point is refracted out parallel. So this is where the image needs to happen in order for us to see it clearly. But my retina is right here. So I see blurry because it's getting all of this information about the top of the retina spread out across a distance. So I need to push the image back. I need help pushing, the image is pushed back. I need help bringing the image forward. So does that happen in a nearsighted situation or a far-sighted situation? That happens in the far-sighted situation. So if I were in water, I'm going to bring up the image again. Let me talk this through first. If I were in the water, this object that's near, I can't see. I can't see this object that's near. But if I take this object and I put it really, really far away from me in the water, then this image is going to get brought forward, possibly forward enough to hit that retina. So I actually become far-sighted when I go into the water. The image gets pushed further back. When the image gets pushed further back, when the image is focused behind the retina, that's a case of far-sightedness. When the image is focused in front of the retina, that's nearsightedness. Should we do another one? Maybe we should do another one. Let's do another one. Let's imagine, these are very tricky. They're very tricky. And it really just, and I even mess them up. We got to go very, very slow. The key is to go very, very slow. Let's imagine that, oh, we have a question. Yes. So Kyle asked, does the image get pushed back in the water because of the change in mediums? Yes, exactly. Because the refractory system is used to an air cornea difference. That is a big difference. When I go into water, the difference decreases, so the amount of refraction decreases. When the amount of refraction decreases, it's as if those light rays can't converge until later, further away, and that image is produced behind the retina. So yes, Kyle, that's a good description, exactly. So Aiden, I'm not sure what your question is. Can you unmute and explain what you mean?
So, like, why does it matter if it's in water or air? Like, I get there's a difference in density, but like, how does that change someone's nearsighted or farsightedness?
It's the effective nearsighted and farsightedness. So it makes it worse. Because of this change in medium, now all of our rays of light are coming through water before they hit our eye. Before they were coming through air before they hit our eye. And the first thing that happens is you get refraction at the cornea. So you get a bending of light. And back in our refraction unit, this is why this material is tough. Back in our refraction unit, we said that the larger the difference in mediums, air to water, is larger than water to water, or air to skin is larger than water to skin. Water is more similar to skin than air is in terms of optical density. The larger the difference, the more bending. So your eyeball can bend rays of light to a certain extent. As soon as I put that eyeball in the water, now it doesn't bend the rays of light to the same extent because there's water in front of your eye instead of air. As a result, it bends it less because there's less difference, less bending. So these rays of light that normally would come together here are bent less, so they come together way back here. And that means the image is formed way back here. So if I could stretch my eyeball and put my retina way back there, I'd be fine. But I can't. That, when images are produced behind the retina and I can't make the necessary adjustments, that is farsightedness. Why is it farsightedness? Because if I move that object further away, the image is brought up naturally. We know that in a convex system, images are produced closer to the focal point, so are brought forward when objects move away. And so it naturally will get closer to the retina, and I'll have, as things get further away, I can see them better and better. So I am far-sighted. So that's how we change our sightedness when we go into water. Now, most people can't make the necessary adjustments in water. That just doesn't work well. So what do? We put goggles on. We make that air boundary exist in our lens system so that light goes from the water into the air, but as it goes from the air in front of our eyeball to my eyeball, I now have an air to cornea boundary, and my refraction is appropriate for it. Those who can't do that in the regular world, so those people who need glasses in the regular world, need prescription goggles if they want to see clearly in the aqua world. So hopefully that helps. Okay, let's see what the next question is. So Christian said, does our sightedness change in different mediums regardless of whether we suffer from sightedness normally? Absolutely. Absolutely. That's exactly the question I just asked in terms of going into water. So if you're normal in air, 20/20 vision is what we call normal. If you're normal in air and you go into water, you will experience what it feels like to be farsighted. Okay, when you go into water, you'll experience what it be to be farsighted. If you're normal in air and you go to space, now the medium becomes larger. We're going from a vacuum instead of air. You'll experience what it feels like to be nearsighted. So yes, a change in medium, our sightedness and how we're defined as sightedness is defined because we live in the air and atmosphere. So absolutely, our sightedness will change because it has to. Now we still may be able to make the necessary adjustments that we need. So my sightedness and your sightedness will be different as I go into water, because I may be able to make the necessary adjustments and you may not be able to make the necessary adjustments, as well as me. But yes, both of our sightedness will change because it's defined as the air. Good questions. Ian asked about bifocals. And bifocals are typically not necessary for young people. This is a very sensitive issue, Ian, because I have to go to the eye doctor in a week. And the last time she told me I was going to have to get bifocals. Yeah, well, the other one is how I feel about it. So you're really bringing up a sensitive subject for me. But why do we need bifocals as we age? Well, accommodation, the ability to focus on things far away and subsequently focus on things nearby and everything in between is entirely dependent on our ability to change the shape of the lens. We change that shape for everything we look at because the distance of the object dictates the distance of the image for a given lens. And I need that image to be produced at a very specific spot on my retina. And so I absolutely have to change it for every location. My ability to do that weakens as I get older. My ciliary muscles, like other muscles, weaken as you get older. So we have less flexibility in that accommodation. And furthermore, the plasticity of the lens itself changes. And so it doesn't bend and stretch as well. So I not only have difficulty thinning it for objects that are far away, but I also have difficulty thickening it for objects that are close. So I need help for both. So on the top is my nearsighted lens. So I can see things, so because I need help with things far away. And on the bottom is my farsighted lens because I need things for things close. So a bifocal lens actually has both properties. Good question. Does saltwater and yes, saltwater and freshwater do have different optical densities because it's based on the makeup of the material. So how much you would be farsighted in freshwater would be different than how much you'd be farsighted in saltwater. And Ian, well, I'll at least be joining. Ian says he also has bifocals, and I'll at least be joining a group of people such as yourself, which are good people. Okay. Any other questions about this nearsighted, farsighted? I'm actually going to not do another one. I'm going to give them to you because I'm looking at the time and I love talking about stuff. So I love all the questions. It's so much fun for me. But I do want to be able to give mirrors because we're going to have to cruise through color on Wednesday. I don't think we're going to have time to introduce color. So I think I hit all of the questions that came in other than, oh no, I hit the bifocal one too. So practice. I'm going to put some extra ones up for practice. So practice. All right. Let's talk mirrors. And we're not going to do as much ray diagramming with mirrors as we did with lenses, but you do need to understand the properties of mirrors. So there are 3 mirrors that we are going to deal with. 3 different types of mirrors. 2 different types of lenses, 3 different types of mirrors. The first mirror is a plane mirror. And notice it's spelled P-L-A-N-E, like a plane, like a dimensional plane. And this is the mirror we're most typically familiar with. So I don't, not that you can see yourself in this, but if I look at, I'm gonna shine a light, you can now see Max, my camera buddy. So Max looks like he should look. He's about this right height. He looks normal, but what other things do we notice about Max? Well, he's upright and he's about the same height as he should be. So if you were to look at me in the mirror, I'm upright and I'm about the same height as I should be. So that's one property, our properties of a plane mirror. So image is upright. And I'm going to say it looks normal. I should have tested how mirrors look to you in this camera. This is sort of fun for me. Okay, so another object that's mirror that we have is a concave mirror. That's going to be mirror number 2. Now, a concave mirror is bowed inward. So now you should see Max. Let me see if you can see Max or the rest of the room. Max is my camera. And what do we notice about it? Well, it's upside down and it's not normal sized. Depends on where we are, and I'm not sure where my depth is. So as I get closer, we should see the size change. It should be getting larger, and as I get farther away, we should see the size change. So we have some properties. That's probably making you all want to throw up. We have some properties of a concave mirror. One is the image is upside down, and it can change size as we move further and closer. I have no idea if this is going to work, but well, if I bring this concave mirror super close, oh, it did work. Now Max should be huge and upright. So as I bring the mirror closer, the image is upright and large. That should sound very familiar. Okay, the last mirror we're going to talk about is the convex mirror. This is bowed outward. And what do we notice about its images? Do you see the rest of the classroom? Well, they should be upright and they should be tiny. They should look far away. Max should look really far away and small. So this mirror the images are upright and smaller than the object. So they look far away. They look far away. Now, I always like to tell this story. I got to see who's all in class today. Not in class today. One of your classmates is a contemporary of my son and actually probably had the same experience as he did. So when my son was in 2nd grade, I used to do a project in this class where you all would have to go out to the elementary schools. Now, not so much of that's happening these days. But his class did a project on mirrors and image formation. And he came out, when I picked him up that day, so excited because he learned that there were 3 types of mirrors. And I asked what they were. He said plane, concave, and convex. And he said a concave mirror is called concave because it bows in. And a convex mirror is called convex because it bows out. And they make really exciting images. But a plain mirror, it's called plain because it's boring and it doesn't make anything exciting. Oh, I thought that was cute. It's not plain because it's boring, it's plain because it's flat. All right, so these are the types of images that these 3 mirrors make, but how? How do they make such different images? Why do they make different images? And for us to appreciate why they make different images, we have to understand what's known as the law of reflection. And this is something many of you already probably have experience with. The law of reflection. If you ever like to go do things like play pool, and it's also similar to our conservation momentum idea. All right, the law of reflection tells us that a ray of light that hits a reflective surface. So here's a ray of light hitting a reflective surface will be reflected such that the angle of incidence, so this is my incident ray. This is the point of incidence. These are the same vocabulary that we had for lenses. The angle of incidence and the angle of reflection, not refraction, but reflection, are the same. Now, it is critical that we remember that that angle is relative to the normal. So this is our angle of incidence. This is our angle of reflection. And in all mirrored surfaces, the angle of incidence equals the angle of reflection. And I'll write reflection out because we use theta r for refraction also. So you gotta know what system you're talking about. Okay, so how does that influence things that we see and images that we see? Well, let's imagine we have a plane mirror here, okay? In a plane mirror, parallel rays of light are all going to be reflected parallel because of the law of reflection. But what if my surface was jagged? What would I see if my surface was jagged? In this case, if I shined a light on a nice flat surface, I would see a nice bright reflection. If I shine a light on a jagged surface, what happens? Well, this ray of light is going to be reflected equal to the normal. This parallel ray of light, well, it's not going to be reflected parallel because this normal is different. So it might be reflected like that. And so on and so forth. And so if I have point sources of light coming in, they're going to hit my eye at different locations. Here, all those point sources of light are going to hit my eye in a systematic way. Here, those point sources of light are going to hit my eye at different locations. Furthermore, if I take this jagged edge, so imagine this jagged edge that has a bowed structure to it, and it's sewn on some clothing. So now I have a jagged edge, so imagine I am not a 3D drawer. So this is 3-dimensional, okay? So it's bowing out and it's on some clothing. And now as I walk around with that on my clothing, light's hitting it, but it's being reflected in all different directions. So what do I look like I'm doing? Shining and shimmering. This is how we utilize sequence. For example, sequence on fancy clothing, fun suit coats. I saw a Christmas suit coat, which was all sequence. It was pretty fun. Or fancy dresses. My wedding dress had 3,000 sequences on them. My grandmother sewed on every one of them individually. She was amazing. I loved her. Yeah, this always be nice to your grandma. So it sparkles because the light is reflecting off of that surface and hitting our eye at different locations. Or what if you wake up one morning and you're out at your cabin and you look out at the lake and it's like perfect barefooting weather. So the lake is super calm. And what do you see in the lake? You see the trees reflected. You see the sky reflected. It's so beautiful. But as the wind picks up and the waves start to become rough, do we see the trees and the sky reflected? Why not? Well, those rays of light are not parallel, forming an image as if the lake was a plane mirror. They're hitting in all sorts of directions, not able to form that image. So I'm going to share an image because this one I really struggle with drawing. So I will choose not to draw it and show it to you. Here is our plane mirror image formation. We see that a ray of light reflecting the top of the candle is reflected via the law of reflection. Now we're going to use a different part of the candle now. So a ray of light reflecting the bottom of the candle is reflected via the law of reflection such that this angle of incidence, this one, and the angle of reflection are the same. And those two rays of light and everything in between hits my eye. Those are the same two rays of light that would hit my eye if that mirror wasn't there. And this candle was located this distance with this height. So I see that image, that virtual image that doesn't actually exist. I perceive that image based on these rays of light hitting my eye being the same as if it were coming from this object. And the geometry of the situation tells us that the distance of the image is the same as the distance of the object, and the height of the object and the height of the image are identical. And the reason that's valuable is because that's that perception in a plane mirror that I look normal. If I'm standing a foot away from the mirror, I look like I'm a foot away from the mirror on the other side. I'm a certain height, and that's reflected in that other side as well. And so a plane mirror produces an upright image that looks normal. Upright images, of course, are always virtual. Upright images are virtual. Now, the law of reflection holds for all of our reflective surfaces, including the concave lens. Concave mirror. So here's my concave mirror. That blue doesn't appear to be coming clear for me. If I draw an optical axis for that concave mirror, bisecting it just like we did for the lens situation, the curvature of this mirror gives rise to its focal point. Curvature gives rise to the focal point in a very specific way. You don't have to remember this, but it's kind of useful to know. It helps frame things for you. The distance between the focal point and the mirror, so the focal length, is twice the difference between what we call the radius of curvature. The radius of curvature is the radius of this circle that I took this mirror out of. So if you imagine this as a giant sphere, the radius of that sphere is the radius of curvature. A focal point is 1/2 the radius of curvature, okay? Now, with a concave mirror, one that has the reflective surface on this inside, if I put an object outside the focal point, a ray of light that is parallel to the optical axis, how will it be reflected? Well, this is the same process we did with refraction in a lens. We would have to draw the tangent. Here's my tangent line. We'd have to draw a normal. That's not even a good normal. We'd have to draw a normal relative to that tangent line. And this is the incident angle. So the angle of reflection is the same as the angle of incidence. And for a concave mirror, that goes through the focal point. So we can see that. I'm going to use my laser ray box again. So I have a concave, this is a mirrored surface on this part of the lens, mirror, excuse me. And we should be able to see that parallel rays of light, you can see them converging to a common point. That is that focal point, okay? So for a concave mirror, a concave mirror converges rays of light. A concave mirror converges rays of light. This is different than a lens. A convex lens converged rays of light. So a concave mirror is converging. And it does so as the result of that law of reflection. Now, if I were to continue in this ray diagramming, rays of light that go through the focal point are reflected parallel. And, gosh, these are really badly drawn lines right now, I'm sorry. Where those two rays of light cross, and all, of course, the other rays of light, is our image location, okay? It's upside down. This is a real image. If I put film at this location, or a screen, or my eyeball, a retina, I get a real image. Eyeball's a little bit different because it has to go through the refractory system, but screen or film. And we do that. We can use concave mirrors to bring light rays from outer space, use them in telescopes to get a real image focused on a screen. So concave mirrors produce real images. Now, they're upside down. So here's my concave mirror again, and you should see Max upside down in this mirror. As I come closer, we saw that Max got larger. As I move farther away, we see that Max gets smaller. Does that follow our ray diagramming? Well, close is large. If I take my image and I move it further, further, this is the same ray of light, of course. This ray of light is reflected parallel, and we see that image gets smaller. As I move inside the focal point, if I bring my mirror really close, we get a flipping over of the image and it becomes large. This is similar to our convex lens. So here's my focal point. If I bring, here's my ray, parallel rays of light are reflected through the focal point. Rays of light in line with the focal point are reflected parallel. These rays of light are never going to come together. Never going to come together. They're diverging. But they'd be the same two rays of light that hit my eye. Same two rays of light that hit my eye as an object large and at a location, in this case, on the other side of the mirror. So my image is upright and it's big, upright and big. All right, we are nearly out of time. The last type of mirror was the convex mirror, the one that goes out. If I replace my concave mirror with a convex mirror, we see that those rays of light spread out and it's tilting, sliding down the thing. So these rays of light spread out. They're never going to converge, ever. But we can still make some sense of them in our visual system like we have been doing so often lately, this interpretation. And they would be the same rays of light that hit our eye if the object was at a certain location relative to the mirror. Upright and smaller, always upright and smaller. So on Wednesday, we'll do a quick ray diagram of that, talk about some of the practical applications, and just review image formation in lenses, okay? Type of image and what it looks like is all you really need to know. We'll put some practice problems on that. And then Wednesday, we will talk about additive color mixing and subtractive color mixing, and hopefully get to colored objects and filters a little bit. And then on Monday, we'll finish that up, and that's when your test opens also. So one topic is going to be probably presented on Monday before your test. It's a fun one though. All right, that's all we have for today. Please stick around if you have some questions you want to follow up with. I can hang out for a little bit. I'm going to put your PowerPoints up right now so I don't forget. All right, good job today. I will stop the recording for anyone who has questions.